have a look at page 83, question 8. Okay, you have a person of mass 60 kg that stands on an accurate bathroom scale placed on the floor of an elevator that operates inside a tall building. At a certain instant, the bathroom scale reads 58 kg. Which role could give you the person's direction of motion and direction of movement and type of motion? Okay. So a person mass 60 kg stands on bathroom scale, placed on the floor of the full building. This is the true value. This is the perceived value. Now this one here, the mass is actually your weight. Okay, the mass and weight are somewhat related. Okay, so the person standing on the bathroom scale, he's actually measuring his weight, but here the weight is not measured in newtons, it's measured in kgs. All right, the 60 kg here can be thought of as being the actual value of the person's weight in kg. This 58 kg is the perceived value of the person's weight in the elevator. In the elevator, in the moving elevator. Okay. So,
yeah,
the question is direction of motion and type of motion. Now, from here to here, from the true value to the perceived value, the person actually became lighter, isn't it? Okay.
yeah,
So this is the case where this is the elevator case that we've done in one of the notes. So if you talk about A and also D, what were we supposed to see on, what would be the change in our apparent weight, in the perceived weight, if it's constant speed? Sorry, I highlighted the wrong thing. If you refer back to the notes that I did for you, there was one part that I went through an example of going inside an elevator. That one was under page 6, remember?
yeah,
The first part was constant velocity outwards. So remember, if it was constant velocity, or in this case, constant speed, there will be no change, isn't it? If you refer back to the notes, I made a derivation, then there's no change, right? Because that time I mentioned to you, if this was the person, this was your weight, this was your reaction force. If you're, even if you're going up or you're going down, if your A is 0, if your A is 0, because constant speed, A is 0, that means F net is 0. That means W will be equal to R. That time I think I drew it like this for you. F net is equal to MA, F net equals to 0. So W minus R equals 0, R will be equals to W. There will be no change. Okay, this one, if it is yeah, okay. I don't think I should make things more complicated. So just know that if the acceleration is 0, net force is 0, the forces are equal opposite on W is equals to R. So this one no change. All right. this is your apparent or perceived weight. Okay. Right, self-plan only leaves you with two other choices. Either you are going downward and slowing down, or you are either going upwards and slowing down. So let's try to analyze B and C. Okay, so this one is for A and B lah. So let's say I thought about for B. Okay. Now you're moving downwards, but you're slowing down. Okay, now this is where I need to kind of do something for you. Okay, now your W is downwards, your R is upwards. Now, if you're moving downwards, but you're slowing down, okay, if you're moving downwards, but you are slowing down, where do you suppose the direction of your acceleration should be? Should it be going up or should it be going down? You're moving downwards, but you're slowing down, okay?
Your acceleration will be downwards.
Okay. Remember what I mentioned to you in kinematics? If your motion is this side, but your A is this side, same direction, you will speed up. But if your motion is like this,
It's upwards.
right? So this one is slow down. So here,
Right.
there's a bit different. This question has some slight variation with what I mentioned to you that time. Okay, although this one is telling you you're moving downwards, but because you're slowing down, your acceleration is actually upwards. Okay, so acceleration is actually outwards. So now if I want to apply F net equals to MA here, R is in the same direction as my acceleration, so it will be R minus W equals to MA. So now R will be equals to MA. Maybe I write it as W plus MA. This one here, your weight is added with MA. So this one you feel heavier. But what you know here is that you are actually becoming lighter. So B is definitely out of the question already. Okay, so here you're supposed to become heavier. All right. So now if I try to double confirm that the answer is C, because you already see A, B, C is wrong, right now the answer definitely has to be D. But let's just confirm whether that is true. So now if I have a case where the object is moving upwards, let me just draw it here. For D, I have an object that is moving upwards, motion upwards, but this one is slowing down, okay? My motion is upwards, but I'm slowing down. So if my motion is upwards, but I'm slowing down, the direction of my acceleration should be downwards, isn't it? Okay. It's a bit similar to this, right? I'm moving up, but I'm slowing down. So my direction of my acceleration should be downwards. Okay. So now I know W is down, R is up. Now if I want to use F net equals 2MA here, it will be W minus R equals to MA. So now R is equals to W minus MA. So now you see your weight is subtracted with MA. Okay. Your weight is being subtracted with MA. So you will actually feel lighter. So answer is D, because here you already see that from 60 kg to 58 kg, you are actually feeling yourself becoming lighter. So the only situation that tells you that you are becoming lighter is D. Okay. Right. So that is one part of it. So good.
Yeah.
Okay. So this one is okay. Then I move on to some other parts of it. Okay. This chapter is not really just all about momentum. There are also some things about force. Okay. I've been doing a lot of things about momentum with you. So now I'm going to try to do something else that is on the forces. Okay. So page 26. Let me see whether page 26 is okay. Okay, so let me just have a look at page 26. Okay, have a look at page 26, question 9. Okay,
Okay.
right. Now, water flows out of a pipe and hits a wall. When the jet of water hits the wall, it has a horizontal velocity of v and a cross-sectional area of A, which is this one here. Okay. The density of the water is rho. The water does not rebound from the wall. What's the force exerted on the wall by the water? Okay, so this is something else. Oh yeah, what's the significance of this statement here? The water does not rebound from the wall. So when your water comes from here and then it hits here, this one might have velocity of v, and then because it does not rebound from the wall, sorry. Basically what it just wants to say here is that it hits the wall with v. All right. Now, if your water hits the wall with velocity v and it does not rebound, the significance of this statement is that your change in velocity is just v minus 0. It's just v. Or put it another way, your change in momentum is just mv minus 0, giving you mv. Remember that little case where I mentioned to you, if you have a mass m hitting a wall with velocity v, and then it rebounds with velocity v again, your change in momentum was just mv minus with negative mv, giving you 2mv. This one was one of the earlier examples on page 1 of your notes. But here, if the situation is that water does not rebound, that means you will have 0 at one other side of the, you will have 0. So your change in velocity is just v, your change in momentum is just mv. Okay, so that one just bear in mind first. Now, the question wants you to find the force. Whenever they ask you to find force, the first thing that usually should come to mind is either this one or this one. Okay. All right. This one is the most basic one that normally should come first.
Yeah.
Your force is actually your rate of change of momentum. So now, if I ask you what is your rate of change of momentum now, my change in momentum is just going to be mv, isn't it? Because here I mentioned this to you just now.
Yeah.
Because it does not rebound from the wall, your change in momentum is just going to be mv. It's not going to be 2mv because the water did not rebound. Okay, so it's just going to be mv over delta t. Okay, now then after that, what you want to do is that notice that it doesn't have the expression that you have here. Instead, you have some sort of expression that has density inside. So what you have to do here is that you want to change off one of the terms inside so that it has density. The easiest thing to do would be to change off the mass, because you know that density is mass over volume. such that mass is equals to density times with volume. Okay, so now we have density, volume times with V divided by delta T. Now, your volume is this one here, isn't? I mean, I try to do it properly. Your volume is actually this entire thing. And this one is your volume V. Now, your volume V will be equals to area A times with length L. Area A, you already know it here. Your length L could be something like this. Okay, so now you can say that rho A L V over T, but then rho A L over T times V, this little thing here is distance over time. Now, distance over time, you remember is speed, isn't it? Speed is distance over time. Remember?
Yeah.
So this one here is actually similar to V. So your
It
result,
just becomes V square.
yes, correct. It become rho
A
A
V square.
V square. So answer is B. Sorry, no, answer is not B. Answer is C, sorry. So your answer is going to be D, sorry. Okay, rho A V square. So this is one part here. Okay, so that part is okay.
Yeah, sir, let me copy.
Yeah, sure, no worries.
Okay.
Okay, right, so that one is okay. Then let me just have a look at something else. Okay, now, it's still on the same page. Let's try to do something that's related to weight. Okay, now, still same page, page 26. It's actually the question before this, the one that you just did. The acceleration of free fall on Pluto is 0.66 meter per second squared. An object weighs 6 Newton on Earth. How much would this object weigh on Pluto? Okay, so weight is mg. Okay, so what you do remember is that mass remains the same regardless of location, but g changes with location. Okay, so what they want now is the weight on Pluto. You have two objects, you have two different places, Earth and Pluto right now. So if you want to find out the weight of the object on Pluto, you first need to find the mass, right? So you can say that on Earth, W is equals to mg, is 6 equals to m times 9.81. So your mass is just going to be 6 divided by 9.81, giving you 0.612 kg. So then on Pluto, W is equals to mg. The weight, sorry, the mass must be the same. It will be 0.612 times with the acceleration of free fall on Pluto being 0.66. You're gonna get this 0.612 times 0.66, giving you 0.4 0 Newton. If I change to 2s, so answer is A. Okay. There could also be another different way of doing this. This is another way of doing the same thing. I just show you first. Now, between the object on Pluto and the object on Earth, okay. Now, when I wanted to find the weight of both objects on both of the planets, you would agree that the equation is W equals to mg applicable for both cases, right? Right? Whether you're talking about the object being on Pluto on Earth, the equation W equals to mg applies for both cases. All right. Now, there's this little method called ratio method that you will notice me using more and more towards the later chapter. So now this one, I just show you a simple example of it. Now, for both of the cases right now, I know W equals to mg applies to Pluto and on Earth. What is common to both the cases? So I know that mass is constant for both Pluto and Earth for both cases. I know G will vary. So now the conclusion I can get here is that M being constant here would mean that weight is proportional to G. So this in turn would mean that weight on Pluto, the simplest form would be just this now. What this means is that W2 over W1 is equals to G2 over G1. If I want to change it to the case of Pluto and Earth, it will be like this. The weight of Pluto to Earth is equals to the G of Pluto to G of Earth. So right now, I want to find weight of Pluto. I know the weight of the Earth is 6.0. The G of the Pluto is 0.66. The G of Earth is 9.81. The weight of the object on Pluto will just be the same answer. You will get back the same answer. Okay, you will get actually with 0.66. Oh, sorry. It's not 0.60. This is 0.66. Okay, 0.66 divided by 9.81 times 6. You again will get 0.40 Newton. Okay, so this is actually another different method of doing this. Okay, this one is ratio method. Okay, all right, so just be aware of this method for now. When you go towards deformation of solids 2 or 3 chapters from now, you will use this a lot. Okay, right, so that one is okay. Then can I move on if you're okay?
Yeah, can.
Right, so let me just find some of the more difficult questions again for you. Okay, page 8, is it okay? Page 8, page 9. What's the speed? Okay, no, maybe we have a look at page 8. Okay, so let me just clear this one off. Okay. Have a look at page 8. Okay, we haven't done until here. You have a golf ball that's hit by a club. Okay, we're looking at question 10. You have a golf ball that is being hit by a club. The graph shows the variation in time or the force exerted on the ball by the club. Which quantity for the time of contact cannot be found from the graph? Okay. So there are some things here that can be found from the graph, some things that cannot be found. They want you to identify the thing that cannot be found from the graph.
I think it's D.
D, the maximum acceleration of the ball. What's missing here that you cannot find, that cause you to not being able to find maximum acceleration?
The mass.
Yes, the mass. Because you see, if you want to find the maximum acceleration is F equals to
MA.
ma. Okay, F is equals to ma. This one, F max can be found from graph, but mass itself is unknown. Okay, actually the acceleration is also unknown. I cannot find out the acceleration from this graph. So this one, D, I cannot find. All right, the maximum acceleration to ball I cannot find. Now, if I want to find out what is the average force on the ball, I can actually find it out. This one is 0. This one is F max. My F average is somewhere around here, right? This one I can find. The change in momentum of the ball, recall that I mentioned to you, force is rate of change of momentum. Okay, force is rate of change of momentum. Force is in turn this one, force times the time. This one is area under force time graph. I can find this too. Now, contact time between ball and the club, I can also find out. It's going to be this one. Okay, so this one is the contact time. I can also find this. So A, B, C I can. D I just can't. All right. So that one is okay. Then after that, question 11. Okay, let me have a look at question 11. Okay, now have a look at question 11, also on the same page. A glider of mass 1,500 kg is launched from rest on a straight and level track using a catapult. The graph shows you the variation time of the resultant force. What's the speed of the glider when the resultant force acting on it reaches 0? Okay, so they want you to find out the speed of the glider when the resultant force acting on the object reaches 0. It's launched from rest on a straight and level track using a catapult. This is the variation with time of the resultant force. Okay, so what can you find from here? What do you think you want to use here? Hang on, let me just okay, here is your little object. Right, and then after that it was at rest, so it's 0 meter per second, and then after that you want to find the v here. Okay, so this one, the time that is elapsed is t equals to 40 seconds. Okay, this one has a mass of m. Okay, now let me just ask you this now. Would there be anything useful that I can find from the gradient of the graph? Anything useful that I can use from gradient of the graph? Does anything make sense if I look at the gradient?
You can find the momentum.
From gradient. the gradient here is force over time. Force over time, does it tell me
Oh no,
anything?
no, no, you can find. Wait, I thought that it would be like the change in momentum.
That one is error, isn't it?
Oh yeah. Oh okay, never mind.
Oh, okay. Yeah, because F is rate of change of momentum. Change in momentum is force times time. This one here is the error under FT graph. Okay, the gradient of FT graph does not tell me anything, you see. It's just force divided by time. There's nothing useful I can get from that. Instead, I want to find the area. Area will give me something useful to work with because it gives me the change in momentum. Okay, this one gives me something much more useful. All right. So this one gives me change in momentum. So I try to find the area first. So now the change in momentum is just going to be the area of a triangle. It's just going to be 10 times 10 power 3 because you have kilonewton multiply with 40. 10 times 10 power 3 times with 40 times with 0.5. You're going to get 200,000 Newton second. Okay. Now you will notice that I always like to write the unit of momentum as Newton second. It's actually the same as kg meter per second. All right. So just one thing for you to know lah. Okay, Newton second is momentum, right? Okay. Now the change of momentum is 200,000 Newton second. What can I say about the momentum change here? Now, would you agree that over here, your momentum is actually 0 at the start when t is equals to 0?
Um,
0 or not 0?
0.
Yes, because it's from rest. If it's
Yes.
from rest, it's 0. Your momentum here is 0. But then you are interested in here, right? So your
Yeah.
momentum here is mv. So now if I ask you what is the change in momentum between these 2 points, is it correct to say it's just mv? It's correct to say that, right?
Yes.
So it's just mv equals to 200,000. Now from here, all you just need to do is you just sub in the values. You already know the mass as 1,500 kg. So it's 1,500 times v equals to 200,000. V is just going to be 133 meter per second. And there you have it. Okay, so this one is question 1133. On number 15P11. Let me double check the answer for you first. Number 15P11. Yeah, answer is A.
Okay.
Okay, then after that, we talk about question 12. Okay, so we look at question 12. Okay, have a look at question 12, the same page again.
Okay.
Right, it's the same page, question 12. It's the last question on the same page that you're looking at. Now, which statement about a ball that strikes a tennis racket and rebounds is always correct? See, what is always going to be correct? So let me just illustrate for you. You have a tennis ball. It hits your racket. And then it rebounds. Okay. Which statement about the ball will always be correct? Now, notice that they are using some terms, very specific terms. They're either referring to the ball or the system. Okay. Now, total kinetic energy of the ball is
I think it's D.
total momentum of the system is conserved. Okay, yes, that is correct. Principle of conservation of momentum tells you that total momentum before collision and after collision will always be same. But recall also that I mentioned to you that that is only recorded for the system. But if you're talking about the components inside the system, the momentum is not conserved. It can change. So right now here, ABC, let's just go through this one. Okay, now, when the ball strikes the tennis racket and rebounds, the collision can either be elastic or inelastic, right? So if my collision was elastic, that would mean that the tennis ball, so let me see, I think I don't do that. Just know that your collision can either be elastic or inelastic. Now, total kinetic energy of the ball is conserved. Total kinetic energy of the ball being conserved means that the tennis ball hits and rebounds at same speed. Meaning to say if it hits at V equals to 15 meters per second, it will also rebound at V equals to 15 meters per second. Now, is this always going to be true? No doubt sometimes it may be true, but a lot of times it won't be at 15 meters per second, right? It could be some value lower, maybe at 5 meters per second, isn't it? So total kinetic energy of the ball is conserved. This one is not always true. You can only have total kinetic energy of ball conserved. Do you recall what I meant by KE being conserved? If you say that KE is conserved, it means KE before and after remains the same. In other words, no change in KE. Okay. So like my case here, if you have a ball that strikes a tennis racket, the only time your KE will be conserved is when the ball hits and rebounds at the same speed. But this one is not always going to be true. What they want is a case that is always true, always correct. So A is out. Now, total kinetic energy of the system is conserved. Now, this one is also not going to be true, right? This one is only for elastic collision. Okay, recall that when you talk about collisions, specifically for elastic collisions, there were some special criteria for them. First one being total kinetic energy is conserved. Second one, relative speed of approach equals to relative speed of separation. Total kinetic energy of the system is conserved. This one is only true for elastic collision, but as I mentioned, your collision can either be elastic or inelastic. So this one may not always be true because it's only for elastic. All other cases, it will not be conserved. Now, the total momentum of the ball is conserved. This one is also not true because, as I mentioned to you last time when I talked to you about this part of your notes for dynamics, remember I gave you some little diagrams on the left side here. I mentioned to you that the total momentum of the system will be constant, but the individual objects in the system will experience changes in momentum. So here, your ball is actually just one part of the system. Its momentum can change. So if the momentum can change, that means momentum is not conserved. So here, total momentum of the ball is conserved. You can say the momentum of ball changes during collision. Therefore, momentum is not conserved. Okay, same thing here when I talk to you about conserve. Momentum conserve, yeah, when you're talking about momentum, it's the same concept. I'm just going to use what I just wrote here. When I say that momentum is conserved, that means momentum before and after remains the same. There's no change in the momentum. So as I mentioned to you, during any collision, the momentum of the object inside the system can change. All right. It's just that the system itself doesn't change. So you say the total momentum of the ball is conserved. This is not true. Okay, so answer is just D.
Okay.
So far, so good. Okay.
Yeah.
So, all right. Strings as shown in figure 3.1. The balls are pulled back and pushed towards each other. When the balls collide at the position shown in figure 3.1, the strings are vertical. The balls then rebound in opposite directions. Figure 3.2 shows you data X and Y during this collision where they show you the mass, the velocities before and after. Okay. And then after that, you notice that there's some negative sign attached to the velocities. This is just indicating to you that it is moving in the opposite direction to your assumed sign convention. They say that the positive direction is horizontal and to the right. Okay. So over here, they want you to use conservation of linear momentum to determine mass m of y. So right now, what you learned from last week was that when you're talking about conservation of momentum, sum of the initial momentum would be equals to the sum of the final momentum. So right now, you just multiply the mass with the velocity to get the momentum, and then you add out the momentum of the individual object. The initial one, you have this one. And this one, I will just write it as 50G. Actually, no need because the diagram is really there. Okay, the initial momentum, the initial one, you take the mass, multiply with the velocity before collision. The 50G here, the 50 grams. This is 50 grams, right? This one also in grams. Okay, let me just show you this one. $50 grams multiplied with the velocity 4.5 plus with m times negative 2.8. Okay, because this is the initial case where we said that it is 50 grams moving at 4.5 meter per second. And then you have another mass m that's moving at negative 2.8 meter per second. This is the initial case. And the after case is that you still have your 50 grams but this one is now moving at negative 1.8 meter per second, whereas your mass m is moving at 1.4 meter per second. This is how you would visualize the collision before and after. So you add up the momentum of the 50 grams and the momentum of the mass m here. Bear in mind that because this is a negative, momentum has the direction because they're vectors. You need to include your negative inside so that you get a negative momentum here. Right, then after that you sum out the momentum after the collision, you will get 50 times with negative 1.8 plus with m times 1.4. So when you just sub in everything, you should be getting something like this. This is 1.4 plus 2.8 m. Then after that you get 50 times 4.5 minus plus with 50 times 1.8. Eventually your mass would be 1.4 plus 2.8. Sorry, 4.5 times 50 plus 50 times 1.8 divided by 1.4 plus 2.8. Then you'll get the answer as 75 grams. Let me just open out the answer for you. This one will be June 15 P21. Yeah, June 15 P21, you get your answer as 75 grams. This one. Now, notice that in my case here, this G is actually in grams, but I did not change it to kg. There's a reason for that. It's because they say if everything here was G and then everything here was meter per second, maybe it's better if I just do it like this. The thing is that, oh, you might wonder why is it that I did not change my grams to kg here, because it's because I recognize from this equation, this side here, it will just be grams meter per second. Grams meter per second plus with gram meter per second will still give me grams meter per second, right? Then the same goes with this one here. I recognize that whatever is on this side will also just be grams meter per second. Okay, it will still be grams meter per second. So what I realized was that the meter per second here will actually cancel off. Eventually, whatever mass that I have will just be in grams. That's the reason why I just left the values here in grams instead of just changing it to kg. Because if I just leave it in grams here, the value of mass that I get will also be in grams. The other units actually cancel each other off. So that's why I left it in grams only. You could also just change it to kg if you wanted to, if you're not comfortable with that. But eventually your answer will be, the mass is 0.075 kg. You will still have to change it back to grams eventually because your final answer here is in grams, all right? So it really depends on you whether you want to change it to grams or not, all right? Okay, now for part B, still explain whether the collision is elastic. Now, when explaining whether a collision is elastic or not, I remember telling you that elastic collision usually only has two things that you need to consider. That one being the total Ke must be conserved and the relative speed of approach must be equal to relative speed of separation. In any questions that ask you to determine whether a collision is elastic, you will always base your explanation on these two criteria. Either you talk about the total KE, or either you talk about relative speed of approach equals to relative speed of separation. Now, the easiest one for you to do right now would actually be to use relative speed of approach and separation. The easiest approach for you right now to evaluate whether this collision is elastic or not would be to use relative speed of approach or relative speed of separation. Okay, so if you just look at this one here, I just change this. Okay, now if I wanted to find the relative speed of approach, I can, just now I already did some simple diagram here. I'm just trying to match it. Okay, so if you look at how the two objects were before the collision, you look at this part only. Okay. Let me just open. Yeah, okay, now this is a lot clearer. Okay, so if you just look at how the both objects were before the collision, notice that mass M and the 50-gram mass were actually moving towards each other. So in your case here, you would, because they're both moving towards each other, remember I mentioned to you your relative speed or approach here would just be you adding the speeds together. Don't bother about the negative, just add the magnitudes together. So you get 4.5 plus 2.8, you will get 7.3 meter per second. Now, if you move on to what happens after the collision, the 50-gram mass will be moving towards the left, whereas the mass M itself will be moving towards the right. You'll notice that they're also still both moving in opposite directions. They're not moving in the same direction. Last week when I mentioned to you, when you want to find relative speed, whenever you see them moving in opposite directions, either them moving towards each other or away from each other, you will always just add out the speed. Unless you see them moving in the same direction, only then you just take the higher speed minus the lower speed. So in your case here, after the collision, both objects actually move off in opposite directions. You will just also still add up their speeds. So relative speed of separation, this is of approach. This one will be 1.8 plus 1.4 equals to 3.2 meter per second. So over here, your conclusion would be that since relative speed of approach is not equal to relative speed of separation, therefore collision is not elastic. That's the conclusion that you can get from here based on relative speed of approach, relative speed of separation criteria. But you can also do something here where you evaluate it based on kinetic energy. This is one way of looking at it. You can also do it in another way, that is by finding the total kinetic energy. What you could do is that if you want to evaluate a different way, you can actually find out the initial total KE. The KE total the initial total KE. You can also write this symbol if you want to. I have a tendency to write it as this symbol, but Some of you are not used to it. You might be better if you use this. Your KE total initial will be half plus with 0.05 times with 4.5 square plus with half 0.075, because this is 75 grams, remember, times with 2.8 square. You eventually get 4.5 square times with 0.5, 4.5 square times with 0.05 times 5, then plus with 0.5 times 0.75. You should get it around 0.80025 joules. Okay, I might be wrong, but you just let me know if I'm wrong. Okay, then after that, your KE total, your final one, would just be half 0.05, 1.8 square plus with half 0.075, 1.4 square. From here, you will get you get 0.1545 joules. Okay. Right, so from here, you can then say that since total KE is not conserved, okay, no, I think we better just write it another way. Since total initial KE is not equal to total final KE, therefore collision is inelastic. Okay, now there's a keyword that you will need to include in your answer. You must mention the word total. Total initial KE is not equals to total final KE, then the collision is inelastic. If you just wrote it as since initial KE is not equal to final KE, therefore collision is inelastic, that one will not be credited. The keyword here is total KE. Okay, so make sure that you have the word total. Right? So this is two different ways in which you will evaluate whether something is elastic or not in terms of the collision. All right, then another one will be for part C. They ask you right now, use Newton's second and third law to explain why the magnitude of the change in momentum of each ball is the same. Wait, let me just see this one. Okay, they ask you to use Newton's second and third law to explain why the magnitude of the change in momentum of each ball is the same. Now, this particular question here is a question that tends to repeat itself over and over again, a lot of times over the years. The exact wording may not be exactly the same, but they still talk about the same thing. So they're asking you right now, why is the change in momentum for both of the balls the same? Now, before collision, both of the balls were approaching each other. Then after collision, they both move off in separate directions, right? Now, there is one part here. So it's a bit messy. There is one part here during collision where the balls were in contact, right? Let's just say somewhere in the middle here. I would say that during collision, that the balls were in contact. This one, the 50 grams, and the mass M, they hit each other. So there was one point in time where they were in contact. All right. Then after they hit each other, they exert a force, then both of the objects move in separate direction. We will look more on the part where they were hitting each other during the time where they were in contact with each other and explain using Newton's second and third law. So let me just draw out the diagram again for you. You have the 50-gram mass, and then you have the 75-gram mass. They hit each other. This is during the collision. Now, under Newton's third law, you will know that the 50-gram exerts a force F on the 75-gram mass. In return, the 75-gram mass exerts a force on the 50-gram mass. Okay, so you would have the forces being equal opposite. Let's just say that this object is A, and then this object is B. I explain it based on diagram first. So I would say that force due to A is equal and opposite to force due to B. Okay, so this part is fine. Then after that, you also know that force is equals to rate of change of momentum. Okay, so let's just go with this one first. Now from Newton's third law, FA is equal and opposite to FB. Therefore, FA equals FB. And then after that, from Newton's second law, F is equals to rate of change of momentum. Therefore, if I look back at FA equals to FB, this will tell me that change in momentum of A divided by the time is equals to change in momentum of B divided by the time. Then after that, I will say that since time of collision for both balls are the same, maybe I write this. This is step by step, right? Rather than writing here delta T, maybe I'll write it TA and TB. Okay, delta TA, delta TB. So here, since time of collision for both balls are the same, therefore delta TA equals delta TB. Now, in that case here, what you will then get is that delta PA is equals to delta TA, delta PB is equals to delta TB. Because you say that the time of collision is the same, this and this are actually the same. You can actually cancel it off. Therefore, change in momentum A is equals to change in momentum B. You can say that the change in momentum is equal and opposite. Usually you would have three questions for this kind of question. Your first point will come from you explaining that the forces are equal and opposite. Your second point will come from you using second law saying that because the time of collision, so your second point will come from Newton's second law, you saying that force is actually rate of change of momentum. And then your third point will come from, since the time of collision for both balls are the same, you say that TA equals to TB, they will cancel out, therefore giving you this. Your momentum change for both of the objects are actually equal and opposite. This is one way of looking at it. The answer that they write in the marking scheme is something like this. When the balls collide, It's actually the same thing. I'll just highlight it for you. They say here when the balls collide, force on X is equal or opposite to force on Y, according to Newton's third law. Force is equal to rate of change of momentum according to Newton's second law. Since the time of collision is the same for both balls, the change of momentum is the same. Okay. Is basically what I just wrote here. Just that what I wrote here is a more detailed explanation. Okay. Yeah. Did they label this? Oh, sorry. They actually already labeled the balls as X and Y instead of A and B. Okay. All right. This one here. Yeah, this one you just change accordingly. All right. This one is, let me change it for you. This one will be object X. This one will be object Y. This is Fy. This is Fx. So I just need to change on some of the stuff. Fx is equals opposite to Fy. And this is Xy. Okay, this is X, this is X, this is Y. And then this one. Tx, Ty, X, Ty. Okay, so just change accordingly, then you should be fine. All right. Okay, so just bear in mind this particular question. This question is quite popular sometimes in dynamics. It's quite popular in dynamics. Every time they'll ask you, explain why is the change in momentum for both of the objects the same. Sometimes you may get only 2 marks for it, but a lot of times it's 3 marks. So if it's 3 marks, usually the points would always be this: the equal opposite force part, the force being rate of change of momentum part, and the time of collision being the same part. Those will account for your 3 marks. Okay, so that is for this part. Then after that, if you're okay with that, then maybe I go a bit on to another structured question just to test your understanding a little. Okay, 70, was it 70? Okay, let's have a look at page 78. We go into something else. Page 78. We still have 2D momentum that I haven't covered. This one I'll cover later. All right, now go to look at page 78, November 19, P21. You have a small remote control model aircraft that has 2 propellers, each of diameter 16 centimeter. Figure 3.1 is a side view of the aircraft when it's hovering. A is propelled vertically downwards by each propeller so that the aircraft hovers at a fixed position. The density of the air is 1.2 kg per meter cube. Assume that the air from each propeller moves with a constant speed of 7.6 meter per second in a uniform cylinder of diameter 16 centimeter. Assume that the air above the propeller is stationary. Show that in a time interval of 3 seconds, the mass of air propelled downwards by one propeller is 0.55 kg. So when you have some sort of aircraft here, this propeller here is forcing air down, okay? So the propeller is forcing air down, is exerting some sort of force on the air. As the propeller rotates, it's actually forcing some volume of air down. It's pushing some volume of air down. It's actually exerting a force on the air. So according to Newton's third law, the air will exert an equal opposite force back onto the propeller. This is what causes your aircraft to rise. All right. So right now, what they want you to find out is that in a time interval of 3 seconds, show that the mass of air that's propelled downwards by just one propeller is 0.55 kg. So there are a few key things that they mention here. All right. You are supposed to assume that the air from each propeller moves with a constant speed of 7.6 meters per second in a uniform cylinder of diameter 16 centimeter. Assume that the air above each propeller is stationary. Okay, the more important one is this statement here, right? So you assume that the air that they propel out, the air that is being pushed down by the propeller is in the form of a cylinder that is having a diameter of 16 centimeter. Okay, it moves, the volume of air that you have propelled down is in the form of a cylinder with diameter 16 centimeter. Okay, so they want you to find out what is the mass of air that they've propelled in a time interval of 3 seconds. They told you that the air is moving at 7.6 meters per second. So what you can do is that you do something like this. Right, you want mass, you have information for density here. Now mass is rho v. Okay, rho times volume. Right now you can actually just do something like this. Mass is rho over volume. Volume is area times height, and then area is pi over 4d squared times h. All right. Now, in a time of 3 seconds, let's just say right now this is your height, h. In a time of 3 seconds for speed of 7.6 meters per second, you can actually find out the height as Vt, isn't it? Because V in kinematics you learn is actually distance over time. Let's just say it's h over t here. H will actually be your velocity times with the time itself. So over here, in a time of 3 seconds, to find out how much has the air moved, the height in which the air has moved, you need to take the velocity with which it's moving, multiply with the time, which is 3 seconds here. So this one will be rho pi over 4d squared Vt. So from which you can actually start subbing in the values. You can put it as 1.2 pi over 4. Diameter is 16 centimeter, change to meter, so this is 0.16 square. Your velocity is 7.6 times with your time of 3 seconds. You should be able to get the answer. Pi divided by 4 times 7.6 times 3, 1.2. Wait, I'm not getting the answer. Did I do something wrong? Let me just open up the answer for you. November 19P21. Oh, sorry. Now I know why. I defined the density wrongly, right? Okay, no wonder I couldn't get the answer. Density is mass over volume. Sorry, just now I didn't notice that. I defined this wrongly, right? This is not the definition of density. Definition of density is mass over volume. So mass is rho v. Otherwise, yeah, other than that, everything still is in order. Sorry. So this one is not correct. It is density times volume. Volume is area times height. So height is actually the velocity times with the time itself. Okay. So you will get the answer as 0.55 kg. Right. It's because I started off in the wrong definition of density. This is not the definition of density. It slipped my mind. It's this one. Okay. Density is mass over volume. So mass is actually the density multiplied with the volume. Volume is actually area times height, and height is actually Vt. So in conclusion, it was this. This one, the area is pi over 4 d squared. This one, the height is actually Vt. And then together, the volume is actually area times height. Okay, so then you get the answer as this. You should get the answer as 0.55 kg. Now, then after that, they will ask you, calculate the increase in momentum of the mass of air in A. The increase in momentum of the air. All right. Now, the increase in momentum of the mass of air in A momentum is actually mass times velocity. So change in momentum is the change in mass times with velocity itself. It can also be written as this. Now, change in momentum is mass times the change in velocity of air. It won't matter which one you're talking about. Okay, it could be that it is the change in mass multiplied by velocity, or the mass multiplied with the change in velocity. It doesn't matter. In your case here, what is changing is actually the mass. Before you start the propeller, there's no mass. In my case here, when I want to write out what is the momentum change, is actually delta m times the speed. The speed here is 7.6 meters per second. The change in mass is from 0 to 0.55 kg. It is 0 because before you start the propeller, you're not moving any mass of air. But once you started the propeller, in a time of 0.3 seconds, you move this mass of air. So your change in mass is actually just 0.55. Okay? So you just take those two, multiply them together, and you get your answer as 4.18 Newton second. That is your increase in momentum. And then after that, they ask you, what is the downward force exerted on this mass of air by the propeller? So if they want you to find out what is the force exerted on the air by the propeller, since you already found out what is your change in momentum, remember that force is rate of change of momentum. You divide by time, then you get the force. So you just take your change in momentum, divide by your time, you get the answer as 1.39 Newton. This is the force that's exerted on the air by the propeller. Okay, so that part is fine. All right, then after that, they ask you, what is the outward force acting on one propeller? So just now I mentioned to you, when your propeller is turning, it's actually forcing a volume of air down. It's actually exerting a force onto that volume of air. In return, according to Newton's third law, there will be an equal opposite force exerted on the propeller by the air. So you already found out what's the force exerted on the air by the propeller as 1.39 Newton. So the outward force acting on the propeller will be the equal opposite of that. It is going to be 1.39 also, just that it's acting outwards now. All right. Now, state the name of the law that explains the relationship between the forces in B2 and the forces in C1. What's the relationship between the force here on the propeller and the relationship of the force here on the air. They are equal and opposite because of Newton's third law of motion. All right, so this one is okay. I believe you also had the next part of the question. Yeah, you also have part D and E. Okay, now determine the mass of the aircraft. For the part here, when you determine the mass of the aircraft, this one is actually a bit related to the next chapter, forces, density, and pressure. But because you've probably gone through it, at least now I can mention it a bit. Now, the aircraft is actually hovering. Okay. They told you that this is the side view of the aircraft when it is hovering. When it is hovering, the word hovering here means you're not moving up or down. You're just fixed there in the air. You're not moving up and down. Okay. So because you're not moving up and down, you're just hovering under the forces and density pressure that you've done in some way. If you're not moving up and down, you can say that there's no resultant force acting on your object. Your resultant force is 0. Okay. So that would mean that the weight of your aircraft is balanced by the force on the propeller. You have two propellers. You already found out what is the force on one propeller, which is equals to 1.39. So if you have another second propeller, it's also going to be 1.39. Okay, so since they are hovering, that means your resultant force will be 0. The weight must be equals to 2 of the forces on the propeller. So you could say that W is equals to 2F, the weight is equals to mg. Then after that, you just submit the values that you just found. You'll be able to get the mass as 0.281 kg. So m equals m times 9.81 equals to 2 times 1.39, giving you 0.281 kg. All right. So that part is fine. Okay, then part E will be your state and explain question. In order for the aircraft to hover at very high altitude, the propellers must propel the air downwards with greater speed than when the aircraft hovers at low altitude. Suggest a reason for this. So what they are telling you now is that if you want to go to a very large height, the propeller needs to move the air downwards with an even greater speed than when it was at a lower altitude. Suggest a reason for this. Now, you would have learned before this that the density of air is lower at higher altitudes. Okay, the higher you go somewhere, the lesser your density of air. So right now, that's the reason why your air needs to be propelled faster downwards. Yeah, let me just write this out. Okay. Now, because at higher altitude, your air density is less, that would mean that you have less mass of air to move. Less mass of air to move means less momentum change. If you want the same momentum change as before, your air would need to move faster. Because let's just say this one, you remember that change in momentum is mass. Okay, let's just say is change in mass times with velocity, right? So let's just say right now, your change in momentum is 100 Newton seconds. The mass of air you move is 50. And then your velocity of air is 2 meters per second. Right now, if you have at higher altitude, you still want to have the same momentum change of 100. Okay, but because you're at higher altitude now, your mass that you can move, the mass of air you can move is now lower. Maybe this one is at 25 now. So you want to still get the same momentum change as before. Your velocity with which you move the air needs to be higher. Maybe it's 4 now. Okay. So this one, let me just write it out. This one could just be, let me just write it out. This one would be 100, could be 25 here, and this one is 4. Okay. So this is relating to this. Because your weight won't change at higher altitude, you'll still be some value. All right. So your propeller will still need to generate the same amount of force to support the weight. But then when you go higher at a higher altitude, your mass of air is less. Because of lesser density, you're actually going to have less momentum change. So less momentum change would mean that your force on your propeller will be less. Your aircraft cannot hover anymore. So in order for you to generate the same amount of force, in order for you to get back the same momentum change that caused that same amount of force, you will need to move your air faster. Okay, when you move your air faster, even though you have lesser mass of air now, you're still getting the same momentum change. Therefore, you're getting the same force to support the weight of your aircraft. Okay, so that one is for this, right? So this is one part. Okay, then another thing that I should do now is your 2D momentum. Or maybe I just do another one before I give you guys a break, then I go with 2D momentum. Okay, just have a look at page 72. It's just something else I want to go through with you before I finish off this chapter with 2D momentum. Just have a look at page 71. Okay, 71, all right. Your beginning of your question is page 71. Just have a look at page 71. All right, have a look at page 71. This one is another question, June 19 P21. Okay, June 19 P21 will be this one. Especially the graph drawing part. Okay, so right now they tell you, a block X lies along a horizontal frictionless surface towards a stationary block Y as illustrated in figure 2.1. There are no resistive forces acting on block X as it moves towards block Y. Okay, and at time t0, block X has momentum of 0.4 kg per second. A short time later, the blocks collide and then they separate. The variation with time t of the momentum of the block Y is shown. Okay. Then after that, you move on to the next page where they ask you what is linear momentum. Define linear momentum. It's just the product of mass and velocity. You could write it like this, or you can just write it as momentum equals to mass multiplied velocity. All right. Now, then after that, use the figure to determine the interval over which the blocks are in contact with each other. All right. When the blocks are in contact with each other, there will be a period of time where when the blocks are in contact with each other, they are actually exerting forces on each other. There's actually a momentum change. What I mean by that is that this one could be your, they still label this block X and Y, right? Okay. So let's go with this. This is your block X. This is your block Y. It moves with a certain velocity V here. This is before collision. Then this one is say during collision. And then this one is after collision. So during collision, block X would hit block Y. Okay. So what will happen is that X would exert a force on Y, Y will exert a force back on X. And then after that, as a result of that, block X and Y will move off after the collision. So over here, let's assume that they move off. Did they tell you they move off in opposite direction? Yeah, they tell you a short time later the blocks collide and then separate. So let's assume that one of it moves like this and then another moves like this. Okay, so determine the time interval over which the blocks are in contact with each other. It will be referring more towards this part here. Okay, when they were in contact. So when they were in contact, they're exerting forces on each other. There will be momentum change. All right. So because force is equals to rate of change of momentum, when you have force being exerted, you will have momentum change. All right. So when they are in contact with each other, they have forces exerted. When you have forces exerted, you will have momentum change. So you can actually deduce from the graph that you're given, for the time that block Y is experiencing a momentum change, this is the time that they were in contact. Okay, because when they are in contact, they start to exert forces on each other. When they exert force on each other, you definitely start to have momentum change. So this is contact time. You'll be 100 minus 60, giving you 40 milliseconds. All right. And then describe without calculation the magnitude of the acceleration of the block from 80 to 100 milliseconds and from 100 to 120 milliseconds. So 80 to 100 milliseconds and 100 to 120 milliseconds. Right, so what they ask you to do right now is to look at 80 to 100, and then 100 to 120. Okay. Now you see this one here, this is a graph of momentum versus time. Recall that I mentioned to you that gradient or PT graph is actually equals to force. So right now, what you see here is constant gradient. What you see here is that you have constant gradient, constant force. Therefore, constant acceleration. Because you also know that F here will be equals to MA. I write it here and F net equals to MA. Right? Because here you see that F net is also MA. These are two important facts. Gradient of your PT graph is your F, and force is equals to MA. So if your force is constant, it will follow that your acceleration will be constant too. So over here, they didn't really ask you to calculate anything. They just want you to state how would the magnitude of the acceleration be. It's going to be constant. Because there's momentum change at constant rate, there's constant force, therefore constant acceleration. All right. And then after that, if you look at the other part from 80 to 120 milliseconds, which is this part here, you can say that this one is zero gradient, zero force. Therefore, zero acceleration. Okay. It's also based on your understanding of these two facts. So this one will be zero. That's all. Okay, because there's no momentum change, velocity is constant, hence no acceleration. It's just another way of writing the same thing. Then after that, they ask you, use figure 2.2 to determine the magnitude of the force exerted by block X on block Y. Okay, what's the magnitude of the force exerted by block X on block Y? They're actually the same, equal and opposite, right? Okay. Just now I drew for you. Maybe I just changed the screen a little, sorry. Just now I drew for you what happens when the two objects hit each other. This part here. Okay. So when both blocks hit each other, they exert equal opposite forces on each other. Although right now the question is asking you to find out the force on, or right now they're asking you to find out the force exerted by block X on block Y. To find out what is the force exerted on block X on block Y, you just need to look at this one. Okay, just now I mentioned to you, when you see your momentum change here, this is the part where you are in contact. Okay, so this is the part where you have force. Okay, this is force exerted by X on Y. Okay, so you find out the gradient of the graph. Just now I told you that your gradient on your graph is actually your force. So you just find out the gradient. The gradient will be delta P over delta T. Change in momentum over change in time. Okay. So the change in momentum is going to be this part here. The change in momentum is this one. This one is your change in momentum. This one is your change in time. Okay, so it'll be 0.5 minus 0. And this one will be 100 milliseconds minus 60 milliseconds. You eventually get the answer as this. Okay, you should get the answer as 12.5 Newton. Okay. Now, if the question someone asks you, what is the force exerted by block Y on X, you just be the same answer here because of Newton's third law. All right. So that part is okay. Now on figure 2.2, sketch the variation of the momentum of block X with time from 0 to 160 milliseconds. This one is a graph plotting that is worth 3 marks. Now your graph shape will look like this. Most people will get up to this part. Okay. The question already told you, let me just highlight a few things here for you. This part here that you see, the original diagram, this is for block Y. They want you to draw the momentum for block X. Now, the first part of the graph for block X, this one you can do because you already know that the momentum was 0.4 kg meter per second. Okay, but then how did these other two lines come from? Now, the key here is this. Let me just divide it out for you. You will agree that if I draw these lines here, this is before collision. This is during collision. And then this part here will be after collision. All right. Now, specifically, let's look at the part where we're talking about before collision. If you're talking about the part before collision, what is the total initial momentum? Your total initial momentum It's just 0 plus with 0.4. So it's going to be 0.40 Newton second only. Now, according to conservation of momentum, your initial momentum and final momentum must be the same. Okay. So before collision, you understood that the total initial momentum is 0.40 Newton second. If conservation of momentum is still obeyed, your total final momentum must also be 0.40 Newton second. So right now, your block Y, notice that there's already a certain value given to you. This one is 0.50 Newton second. So right now, you know that momentum of X plus with momentum of Y must be equals to 0.4 Newton seconds. This one is for this part. Okay, the final momentum must equate to 0.4 Newton second. But momentum of Y itself is already 0.5. So Px plus 0.50 equals to 0.40. Px will actually be negative 0.1. It will actually be equals to negative 0.10 Newton second. That's the reason why this line is here. This is at negative 0.10. It's because when you add up negative 0.1 and 0.5, you will get back the final momentum as this. Okay, that's the reason why this is there like this. And then once you've drawn this line here, you start to draw this other line. You join these two. Okay, you already drawn this line and drawn this line, right? So what's left is just for you to join the two lines together with the diagonal line. Okay, so this line here is the remaining line. Okay, now you'll notice something a bit special about this line. You notice that the original line here and this new line here the gradient is equal but opposite, right? One is pointing upwards, one is pointing downwards. And then if you look at the steepness, the gradient magnitude, they're actually the same. Here you see that the gradient is equal but opposite. It actually implies force is equal opposite too. Remember just now I told you when the two blocks were in contact, the forces will be equal opposite. This is actually being shown by the graph here also. Okay, so this is how you deduce from the graph.